Lasers. The word comes from a description of what lasers do. They perform light amplification by the stimulated emission of radiation. If an electron in an atom absorbs energy, perhaps in the form of a photon, as I'll show in a moment, or through heating or collisions due to an electric current, it can go to a higher energy level. We say it is excited. I've shown the higher energy level in red and the lower energy level in blue. It will soon, however, go back to a lower energy level, releasing a photon, like this. In a laser, a substance called the amplifying medium is given lots of energy, raising many of its electrons to higher energy levels. This is called pumping. So this is a lamp which will light and raise the electrons to higher energy levels, like this. If we have more electrons in excited states than in the ground state, so the number of electrons in the higher state 2 is greater than the number of electrons in the lower state 1, we have what's called a population inversion. This is essential for a laser to work. As a photon passes another excited electron, it can stimulate it into releasing its own photon, exactly in phase with the first photon. So this electron goes down to the lower energy level, releases its photon, and this one releases its photon in phase. I'll just do that again. If we place mirrors at each end of the amplifying medium, the photons will pass back and forth, releasing more and more photons, all in phase with each other. This makes laser light coherent. They actually have a full reflecting mirror on one side of the amplifying medium and a half mirror on the other side. So if we have a photon travelling along, it stimulates release of another photon. Some of the photons will escape through the half mirror, some will come back to stimulate more photon release. So we get a situation a little bit like this, where we have lots of photons released, they stimulate more photons, and some of the photons escape through the half mirror, some come back to start the process again, releasing more and more photons. So far I've talked of there being two energy levels, N1 and N2. But in a laser, photons are being absorbed as well as being emitted. For any light amplification to take place, there must be more photons emitted than absorbed. If there are just two energy levels, at most we can get the same number of electrons in the excited state as in the ground state. This is not a population inversion, and there will be as many photons absorbed as emitted. To get a population inversion, we need at least 3 energy levels. So here we have 3 energy levels, level 1, level 2 and level 3. The pumped transition takes electrons from level 1, the ground state, right up to level 3. But they will quickly drop down here. This involves no photon, but will involve some heating. There will then be a delay before they drop down here, releasing the photon. Something like this. So after pumping, the electron is raised to level 3, quickly drops to level 2, then a delay down to the ground state. Once more. Pump to level 3, straight down to level 2, and a delay before dropping to level 1. As there is a small delay before electrons drop from level 2, we can create a population inversion, with the number of electrons in level 2 being greater than the number of electrons in level 1. More often, a laser will have 4 energy levels, and the pumped transition takes the electrons from the ground state up to level 4. They then rapidly drop with no photon release to level 3, though there will be some heating. There is then a time delay before they drop from level 3 to level 2, and then they rapidly, with no photon release, drop down to level 1. It's this transition here from level 3 to level 2 which involves the release of photons. So we get something like this. Pump to level 4, straight down to level 3, delay before they go to level 2, then straight down to level 1. Just show that once more. Pumped to level 4, straight down to level 3, drop to level 2, and then straight down to level 1. Electrons rapidly fall from level 2 to level 1, making it much easier to produce a population inversion where the number in level 3 is greater than the number in level 2. Another type of laser which is becoming increasingly common is the semiconductor diode laser. This involves two slabs of semiconducting material. One is called a p-type semiconductor. It has a deficit or lack of electrons. These are known as holes. It has an n-type semiconductor that has surplus electrons. And in the middle we have what's called the active layer. If an electron jumps across to a hole, it releases a photon, like this. As this photon passes other electrons, it can stimulate them into jumping across and releasing their own photons in phase with the original one, like this. So this will be the first electron to jump across. As it passes the others, they all release their own photons. Just do that once more. The right-hand electron jumps across, and as it passes the other electrons, they all are stimulated to jumping across, releasing photons in phase with the original one. Adding a power supply of around 3 volts, we can maintain electrons and holes ready to produce more and more photons. The pumping needed to maintain a population inversion in a standard laser makes them very inefficient, less than 1% efficient, and typically down to 0.01% efficient. Semiconductor lasers, however, can be up to 70% efficient. Semiconductor lasers cannot produce very powerful beams, and so cannot be used for jobs like cutting metal, for instance. They are, however, small and cheap to produce, and, as we've seen, much more efficient, and are used in CD players, DVD players, telecommunications using optical fibres, for barcode readers at the supermarket, laser printers, and many other jobs.